All right. So we're going to walk through these examples. We can answer those other two questions too. Thermodynamic control is guided by the stability of the product, and then kinetic control is the reaction rate. And the kinetic control gives product based on what's the rate. So thermodynamic control is dealing with equilibrium, kinetic control. This is from the previous section, by the way, when we talked about addition of HX to a conjugated diene. So let's look at these questions here, and then we're going to work through several of these examples back here. And then we'll be done with the Diels-Alder section, and we'll start on aromatics on Friday. All right, so let's just walk these down right quick. Let's take number one. Let's take the 1 and 2 and 3 first. 1 and 3. Those are the forward reactions, and then we'll talk about retrosynthesis of Diels-Alder products. So for 1, you can see right now, right there. Hold up. Right. That's how this is a standard Diels-Alder cycle addition. Nothing special about it. What's the product? What does the product look like from that Diels-Alder 4+2 cycle addition?
You would have 3 cyclic rings.
Great. 3 rings here. This one is still intact. And then you have a new, let me fix that up. That's sloppy.
And then that last ring is going to have that double bond.
Yes. The third ring that we added. Let's start from this side, from here. Like so. Right, anybody not see that? Right, so this is the 2 new sigma bonds and the pi bond that got shifted over because of the 4+2. All right, let's look at number 3. Now here we got to take a couple of things into account. Right, number 1, of course, my diene is conjugated with carbonyl, so that's going to speed the reaction up. Anytime I add an acceptor to the diene, it's going to lower the energy of the LUMO and make the reaction go faster. Right, so I have an acceptor here, and then I have my diene, and then this is my dienophile is trans, right? So what that means is what for this reaction? What's the term that is going to help us to understand what the product should look like?
Would it be, since it's trans, it would be a exo product, or we're not there yet?
Not quite. But I'm glad you said that because that gives it brings that up. Remember the reaction is stereo specific. That's the term I'm trying to pull out. So that means that if the 2 groups on your dienophile are trans here and here relative to the double bond, right? You see how the groups on opposite sides of that alkene. Then in the product, you're going to get, just put the arrows in here, here, not there, here, right? We're going to get a 6-membered ring, of course. Alkene is shifted to here, but the groups are trans to one another on the product that we made from this cycle addition. But the thing about this is that's one stereoisomer, but there's no bias like in the starting material. It's not chiral. We don't have a chiral catalyst, so we have no bias in the transition state. So we're gonna more than likely get both this product, the first product that's drawn, and this one, right? All right. So now let's go to the retrosynthesis problems 2 and 4. Right. So with the retrosynthesis, we have the product. We're just going to work backwards. So the easiest way to think about this is to start at the pi bond. Right. It's the same flow of electrons. It's pericyclic, so the electrons are not going to flow outside of the system. So here, here, and here. Right. When we break that up, what that's going to do is put a pi bond here. Here, and here. Right. So in the starting materials, you can see right away, this is going to be your diene here. And then this is going to be your dienophile. All right. What about number 4?
Would that make the pentagon, that part with the O, with the oxygen?
Yeah, so we can start right here. Like that, and then these electrons are coming here, like that. Right, but we don't touch those bridgehead carbons, and I'll show you why. So in the starting material, I have this. Right, it's trans because these groups over here are trans, and the reaction is stereospecific, so it's got to follow that. So those are trans. So over here, that dienophile has to be trans, right? For my diene, it looks like this. Right, so when we use a cyclic diene, we end up with a bicyclic product. Where the two rings are fused together. Right. We'll look at some more of these in the examples that are underneath here. So let's answer 5A and 5B, and then we'll move on to some other problems. It says, which product forms fastest when you compare 1 and 3? What are we comparing? We can look at both the diene and the dienophile, but in 1 and 3, the diene is the same. So we have to look at the dienophile and what can we do to a dienophile to make it more reactive. So the top dienophile here, when you compare it to that top dienophile will be considered electron rich. Right, that's going to slow the reaction down. We just mentioned it a second ago, but I'll mention it again. In number 3, That's the item file is substituted with an acceptor. Or an electron withdrawing group. That's another term for that. I think we talked about that on Monday. So it has an electron withdrawing group attached to it. And so that's going to make that diena file much more reactive. All right. We've already done, no, we haven't. What would the second product look like for reaction 4? We just talked about this with reaction 3. Not endo and exo, but the
VR will be wedged and the OH will be dashed.
you'll have a second isomer. Looks like this. Because again, there's no way to bias it to make one or the other unless you start with use a chiral catalyst, or unless you use a chiral start material. And neither one of those compounds is chiral. All right, let's go down and do let's look at 1651. Let's try to work through A, C, D, E. Let's do that. All right, for A, what do we need to do first?
Rotate the diene.
Good, excellent. The diene is not in the right conformation. It's in a S trans. We need to make it S cis. So that's my diene, and then this is my diena file. I'm gonna draw it like this. And I'll just put a ring inside that aromatic. Right, so this is my diene, this is my diena file. Can somebody put the arrows in and let's see what the product is gonna look like. Okay. Great. So that product is going to look like this. And it's going to have the aromatic ring here substituted on the ring. Excellent. It would be better if I can get my handwriting together on a Wednesday. All right. Let's look at C. So this is my diene. All right, and it's going to be sped up a little bit because those methyl groups are inductively donating. So they're gonna make that reaction a little bit, make that dying a little bit more reactive by raising the energy of the HOMO. Let's see, OCH3. All right. What do we have to think about with this example? What's the stereochemistry of the dienophile?
Is it trans?
In this case, look at the groups. Here's the double bond, right? And they got both groups on the same side of it. You see that?
Mhm.
So it's going to be cis. Trans is when the groups on opposite sides. And then cis is when the groups on the same side. It can be up or down. It doesn't matter, but all right. So in the product, that's part of it, right? And then the other part is, hold up. That, and then like that, right? Oh, no, my bad. Right, so if it's cis in the star material, then the products have to also be cis, right? And then just like you get that product, you can get the other cis product. But they're both on a wedge. All right. All right, let's look at before we do D and E, I want to look at F. Because F is an interesting problem because here it says excess. Right, you got excess diene. Then you have a dienophile that actually has an alkene on each side. All right. What do you think that means if we add in? So let's say, for instance, this is 2 moles and this is 1 mole. What do you think that means in terms of the reaction? If I got 2 dienes.
Is it going to happen twice?
Yes, it'll happen twice and it'll happen on each side. You follow? All right, so that's that. All right, so I'm going to end up doing the 4 + 2 twice. Here, here, and here, and then the same thing here.
Does it happen at the same time?
It's probably really rapid, not necessarily simultaneous, but that's not to say that it can't. But the first reaction and the second reaction probably happen really close together. Maybe not simultaneously, but very, very close together. All right, so then what would my product look like from that?
Bicyclic?
Is it tricyclic?
No, bi. Or maybe try.
Yeah.
Maybe try, maybe buy, about that. So that's that. But you want to have the same motif on the other side, right? right? But the fact that the diene is present in excess means that if there's more than one dienophile, it's going to react with that, right? That's why I wanted to do that problem, because you got two dienophiles in the same molecule. All right. So this is what the product would look like for that. All right, let's do D. It looks intimidating, but it's really not. That's my diene, and then my dienophiles. Here. Can somebody put the arrows in for that? It looks like it's going to be like, you know, something difficult or very intimidating, but it's not. You're going to get the same, it's the same mechanism and the same outcome. Do we need to number it? Will that help?
Yes.
All right, let's put the numbers in. That's 1, 2, 3, 4, 5, 6. So this is where one of my sigma bonds is going to be, right here, between 4 and 5, and then between 1 and 6, and then the pi bond is going to get shifted between 2 and 3. Right, so is the product going to be a 6-member? The core product going to be still be a 6-member ring?
Wouldn't it be a bicyclic product?
Yeah.
Because the
It is going to be bicyclic. It's actually going to be tricyclic, because you started with 2 cyclic molecules, and then you're going to cyclize between them. There's going to be a ring between them as well. So let's see what this is going to look like. So let me just draw it this way. Uh-oh, don't want to do that. Let's do this. So this is my 6-member ring. And then that's connected to this. Like so. Are y'all following?
Yes.
Is 1, 2, 3, 4, 5, and 6. All right, and then I have an alkene here. And then you can see between 1 and 4, right? There's this bridge. I didn't touch that. So I can just draw that back in. I'll leave it in black. Right? I can draw that part back in like that. So the way this would look as in 3D, it's going to get cut off too. Shucks. Let me shrink some of this down so I don't have to move it. Man, I hate it when that happens. All right, let me fix this back first. All right. So we go down here. We were to draw this in 3D. Move this over. Right, it would look something like this. So here, that's that 5. That's 1 through 4, right? Let me start over here. 1, 2, 3, 4. And then you have a bond to 5 and 6, which is here. That's 5, and that's 6. And then that's connected to that 6-member ring like that. Right, so this is a 3D depiction of what that would look like. Right, and notice the bridgehead is, which is right here. Right, that bridgehead is a consequence of the fact that you started with a cyclic diene. Right, so you're fusing these rings together. So this is the 3D version of it. It actually looks like the bridgehead gets kicked up because of the transition state. Right, you think about the transition state. I'll put it on this page. It's going to look something like this, right? Where this is the HOMO of my diene, and then this is the dienophile, right? So when these things come into contact with each other, this carbon right here at the bridgehead is going to get pushed up. If the dienophile comes in from the bottom, right, this is going to get pushed up this way. Right, so that's why it looks like that carbon is facing upward, and that's why it looks like the other part of that is underneath that. Right, and this is an example of what we call it's actually tricyclic because you got 3 rings fused together, but this would be an example of where you would see what we call endo and exo. We got another example we're going to look at for that, but this is one of those examples where you actually see that. So let me go back to, let me find that other example. Yeah, right there. Let's do E. E is a similar type of problem because you start with a cyclic diene, and then but you have an acyclic dienophile. So let's see what that would look like. So I'm starting out with this. Is that right?
No. I think that double bond
Yeah,
that
it's a
radio's at the
ketone.
bottom. Yeah, ketone.
Yeah, it's a ketone. Not, I had it as an aldehyde. My bad. So that's that. Right. So let's just number it, just like we did everything else. So 1, 2, 3, 4. That's let me keep it consistent. That's 5, and that's it. That's 6. So my participants in the reaction, this part right here is not going to participate. Right. This whole piece. Right. That's not involved. It's going to end up getting either pushed up or pushed down in the product, but it's not involved in the reaction. The reaction is going to happen right here between, you know, the 4 carbons of the diene and the 2 carbons of the dienophile. All right, so let's put the arrows in. That's going there, there, there. Right. So in the product is going to look like this: 1, 2, 3, 4, and then 5 and 6 are going to be here. Everybody agree with that?
Yes.
Yeah.
2, 3, 4. And it's just, again, the reason why we're doing it this way is it's a strategy, because when you see it on an exam, you need a strategy for how to attack these problems, especially if you are unable to draw them in 3D, or it looks weird to you and it confuses you. you at least need a strategy to come up with how to draw it in 2D. I'm gonna show you the 3D depiction as well, but all right, so between 2 and 3, I got a pi bond here, and 1 and 4, there's a 2-carbon linker, right? Right here and right here. So I'm just gonna put those 2 carbons back in. So that's a carbon right there, that's a carbon right there, and that's a carbon right there. Clean that up. Right? So those 2 carbons that were over in the star material are still here. Right now, and I need to put a substituent in on 6. Here, this is an example of where we would see what we call endo and exo, right? So now I have this is one of my products. And then the other product will be that same ring system. But the carbonyl would be here. Keep the same color. Like that. Right, so that's going back into the page. Now, if we drew these in 3D, right? This is what it would look like. So I'm gonna draw this out like this. Like that. And then with one of these, you're gonna have the carbonyl here. And then with the other one, I'm just gonna steal this. The other product, you'll have the carbonyl here. Right, and then let me fix that bond. Right, so your carbonyl is actually underneath that ring system. Right, this is what we call exo. And then this one is what we call endo, right? Exo means outside, endo means inside. So that carbonyl is underneath this ring system. And because of that, you can get some extra stability. I talked about this above. I'm going to talk about it again here. You can get some extra stability from orbital overlap. Let me not do that. Change colors with that. Right, so these p orbitals are actually able to overlap. They can talk to one another. Right? It's what we call a secondary orbital interaction. So that's going to stabilize the endo product. Right? So even though there's no bias to favor one over the other, the fact that the endo is lower in energy, right, is going to make it the favorite product. All right, any questions about that?
I have a question.
Go ahead.
So is it gonna have like different product distributions or is still 50-50?
Well, that's a good question. The fact that the endo is favored, you probably will get like a little bit more of it. Just because of the fact that you have that interaction, that secondary orbital interaction. But it's not going to be like, 95-5 or something like that, some huge ratio, because you still have no bias like in the transition state to favor one of those stereoisomers over the other. But you will get a little bit more of the endo. Yes, that's a great question.
Okay.
Mhm. Hope I answered it sufficiently.
Yes, you did. Thank you.
All right. Okay, so let's look at we got 1 minute left. Let's look at one more. Let's see if we can do one more. Because that all of those. That's all of them. Finish this today. We're gonna on Friday, we're gonna start out here doing some retro. We're gonna only do a couple of them, and then we're gonna move into aromatics because it's 9:50. And then I'm gonna have you do this one on your own so you can already start thinking about it. All right. Any questions? Any other questions about anything? The video and notes and all that stuff won't be posted until later because I got another class after this, and then I have to be in Tuskegee for lab. So